Hello and welcome back to Manifolds, the video series where we talk about the general concept of integration on generalized surfaces called manifolds. And indeed, in today's part 58, we will talk about a classical result which is called Stokes' integral theorem. And the name already suggests that this one is related to our generalized Stokes theorem for manifolds. In fact, it's quite similar to Gauss's integral theorem, but we will see that this special one of Stokes only works for two-dimensional manifolds. So it's quite special, but still really important in applications like we have them in physics. However, before we formulate the theorem, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, on Steady or Patreon you can buy a supporter package to access additional material for all the videos. For example, there you find PDF versions, early access and quizzes. And then without further ado, let's immediately consider a two-dimensional manifold inside the three-dimensional space R3. And as always here, the manifold is allowed to have a boundary. So for example, it could be something similar to a half sphere where we have the boundary there. So here we have a two-dimensional manifold M with a one-dimensional boundary del M. And in addition, you might already know that we need an orientation on both things. In other words, we have to assume that the manifold M is orientable. And as we have already learned, this means that there exists a continuous unit normal vector field on M. This means on each point on M we can find a normal vector and let's call it n. And in fact, fixing an orientation on M is the same as fixing a continuous unit normal vector field on M. Hence, in Stokes' integral theorem, we just assume that we have such a normal vector field given. And then it's also important that the boundary inherits its orientation from the orientation of M. And since the boundary is a one-dimensional manifold, we can use tangent vectors on it to describe the orientation. On each point you can put a unit tangent vector and then we also have a continuous field. And we can roughly state that the direction of this tangent vector field on the one-dimensional manifold is given by the right-hand rule corresponding to our normal vector field. And in order to keep it simple, let's denote our unit tangent vector field by t. There, please note, this one is only defined on the boundary of M. Very well, and now since we work in R3 anyway, we can make this right-hand rule really precise. There are different possibilities to do it, but maybe the easiest one is just to take the right hand with this orthogonal system given by the thumb, the index finger and the middle finger. And then you just take the normal vector as the first vector and two tangent vectors as the other ones. More precisely, on the index finger we should have a tangent vector that is outward pointing, and on the middle finger we find our tangent vector on the boundary. So here you should know, outward pointing tangent vector on M means that we have a tangent vector that comes from the surface M but then goes to the outside world. So for example, at this point here, we would have a tangent vector that goes in this direction. So you see, by having these two vectors, we can find the direction of the tangent vector on the boundary. So there we have it, this right-hand rule is a good calculation device if you work in applications. Of course, in our theoretical approach here, we don't need to do that because everything is given in the concept of orientation anyway. So after fixing all the notations we need here, we can finally talk about the formulation of Stokes' integral theorem. So this is the classical Stokes theorem, which is just a special case of our generalized Stokes theorem. And in fact, this one can only be formulated for two-dimensional surfaces in our three-dimensional space. The reason for this is that we actually need the curl of a vector field here. And moreover, since we want to apply our generalized Stokes theorem, we need a compact manifold here. So now you see all the assumptions here. We need compactness and orientation and maybe a boundary for our two-dimensional manifold. And in addition to that, we need a smooth vector field, which we can call V, and let's say it's defined on the whole space R3. And then, as you might already know, we get an identity concerning two integrals. On the one hand, we have the two-dimensional integral over M, and on the other hand, the one-dimensional integral over del M. And now the thing is, in the surface integral on the left-hand side, we find the curl of the vector field V. So at this point you see that we need that the partial derivatives of V exist, and they should be at least continuous such that we can do the integration. And now what happens is that we form the standard inner product of this curl with the unit normal vector field. And then we just integrate that by using the canonical volume form of M. And the notations we use here are just omega M for the canonical volume form on M, and this big dot for the standard inner product in R3. Usually you would write pointed brackets for the inner product, but because this dot is very common in applications, I also use it here. Okay, so there we have the left hand side, and now this integral is equal to an integral over the boundary. Hence there, the canonical volume form of del M comes in. And moreover, instead of the curl of the vector field, we just have the vector field V itself. But since we also have to transform that to a scalar function, we have to use the inner product again. And there we finally use the unit tangent vector field on the one-dimensional boundary. And there we have it. This is Stokes' integral theorem, where the curl is on the left and the vector field V on the right. So a two-dimensional surface integral is transformed into a one-dimensional line integral. And at this point I can also tell you that especially in applications, these two things at the end of the integral are put together. And of course the reason for that is just to get a short formulation out. This means you would write the curl of the vector field here in the inner product with the vectorial surface element. And often this one is denoted by sigma, and to make it clear that this one has the unit normal vector field included, we put an arrow on top. The mathematical meaning is the same as before, but as you can see, it's a shorter formulation. And exactly the same thing we can do on the right hand side, but there we use an S to denote the one-dimensional line element, and also with an arrow to make clear that the tangent vector is included. So there we have it, and I can tell you, especially in physics, this is how the classical Stokes theorem is stated. And now maybe the only thing missing in our explanation here is the definition of the curl of a vector field. Indeed, this is a special definition that only works in R3. And there it's important to remember that the curl of V is again a vector field, so a mapping from R3 into R3 again. And it's just calculated with the partial derivatives of V in a cross-product way. This is why the curl can only exist in R3, because only there the cross-product makes sense. So let's quickly state the definition here. First we have the partial derivative of V3 with respect to x2. And then minus the same but the other way around. This means the partial derivative of V2 with respect to x3. And the whole thing repeats for the other components, just with different indices here. For example, in the second component here, we have to combine x3 and v1. And finally, in the third component, we have the indices 1 and 2. So this is the definition of the curl of a vector field as we have discussed it already in part 50. In fact, we can use this knowledge of the curl to transform it into a differential form where we can actually apply the generalized Stokes theorem. This might not surprise you, because this is actually what we need to do in the proof today. And first of all, always imagine that we have our surface M and the boundary del M. And this already tells us that we actually should consider two inclusion maps here. First, M is a submanifold in R3, so it's embedded in the space. And now this identity map as an embedding we will just call J. And second, the letter I we use for the embedding of the boundary del M into M. So you already know these simple maps are only there to make the objects act on the correct space. So for example, the volume form of M can be expressed by the volume form of R3. And there you already know, The volume form in R3 is just the standard determinant in this vector space. So this measures volumes, and in order to measure areas on our two-dimensional manifold M, we have to put in the unit normal vector n. And now by definition, this is a differential form on R3, and to make it to 1 on M, we have to use the pullback of J. So often one omits writing down this trivial pullback, but here we will do it because it's important in our proof to see what actually happens. So let's quickly go to the picture on the left now, and there you see whenever we want to measure an area on M, we can extend it to the third dimension to measure the volume in R3. Therefore in the formula we just get a determinant where the first column is already occupied by the unit vector n. Therefore the two other columns are still open for tangent vectors from the tangent space of M. This means we could actually put arbitrary vectors in and then do a Laplace expansion along the first column. Then we get a whole sum out, and for example the first part would look like n1 times the subdeterminant here in the right bottom corner. And this 2 times 2 determinant can actually be written as dx2 wedge dx3. This combination here gives us exactly the correct components out. And now you know, continuing this Laplace expansion gives us 2 more terms. The next one will be minus n2 and the last one plus n3. And moreover, you also have to calculate the correct subdeterminants. So in the end, this is the general formula we get for the volume form of M. And in addition, you might already recognize that we can shorten this whole formula by using the standard inner product in R3. The only thing we need to do for that is to put these differential forms into a 3-dimensional vector. So you see, this is just a formal short way to represent the formula from above. And moreover, please note, we exchanged the wedge product in the second component here to get rid of the minus sign. Also, you can directly spot the similarity of this formula to the curl above. However, before we discuss the details there, let's first write down a formula for the volume form on the boundary as well. And please note, there we now measure a 1-dimensional volume. The idea here is the same as always and similar to before, and we just have to use an outward pointing tangent vector from M. And as the other tangent vector, it has to have length 1, and let's call it t tilde. So you see, in order to measure the 1-dimensional length, we extend the whole thing to a second dimension. So as before, t tilde is just put into the volume form of M. And as you already know, to make it formally correct, we have to use the pullback with I. And now you should see that the whole thing is not complicated at all, because omega m is already given by determinant, and now we put in t tilde as well. This means t tilde comes now into the second column of the determinant. However, at this point please don't forget, n, t tilde and t are all mutually orthogonal to each other. So by putting t into the last column of the determinant, we actually get out 1. Please also check that this one is compatible to our right-hand rule. In other words, if we scale the vector t by alpha and put that into our volume form, we get out this scaling factor alpha. And you might know that we can get this scaling factor back when we use the inner product with t. So the whole thing comes down to an orthogonal projection onto t with respect to the standard inner product. And therefore we don't need to write the whole determinant, we can just write an inner product with t. Hence we have t times any vector we can put in, and this one can also be expressed by our differential forms. So quite simple, dx1, dx2, dx3. And with that we have our 2 nice short formulas for the 2 volume forms that we consider here. And now we can finally connect that to the curl of a vector field V. And for that please recall part 50, where we have already calculated a Cartan derivative of a vector field related to the curl. More precisely, we should say that we have a 1 form that is given by a vector field V. And now the Cartan derivative of that gives us the curl of V back. In fact, what we can do is to reorder these two forms that come out such that in front of it we have the components of the curl. So first we have the first component of the curl, then the second one, and finally the third one. This was the calculation we have done in part 50, and it just used the definition of our D operation. However, at this point we can see by comparison to the calculation above that this one is actually just the curl put into the determinant in 3 dimensions. And this is finally what we wanted to have, because now we can use differential forms to transform the curl inside our integral. And moreover, you also see that the inclusion map has to come in because we only want to work on the surface M itself. This means what we will do is to decompose the curl into 2 components. To see this in a picture, let's say that this arrow here is the curl of V at this point. And now we can decompose it orthogonally into 2 components. And only the one that goes into the direction of n should matter here. So let's simply say this one is curl of V with index n and the other one with index t. So this is the orthogonal decomposition of the curl of V that we need here. And then we just use the result from before, but then we also apply the inclusion map J to it. And together with the decomposition, we actually have 2 parts here. The one part is the projection of the curl of V onto n, and the other one the projection onto the tangent space of M. Which means that here in the second part, we have a determinant where we put in 3 tangent vectors of M. So in the columns we have 3 tangent vectors, but the tangent space is only 2-dimensional. This means the only possibility for the determinant here is to give out 0. In other words, the second term completely vanishes and we only have to consider the first one. This is quite nice because it tells us that we can actually use this volume form from above. So omega is essentially given by the vector field V. However, as before, we can shorten this notation by using the inner product with the differential forms. Of course, this is just a short notation for us. It means exactly the same thing as before. Moreover, we already know we want to have a differential form on M, so we have to use J star as well. However, this does not change so much because it commutes with the D operation anyway. This is the naturality, and we see what we get out for the D operation applied to this one form is exactly the result from before. And by the calculation we have done one line above, we know we don't need to use the full curl of V, but just the orthogonal projection onto n. And there, as you might know from calculation in Hilbert spaces, is that orthogonal projections can be expressed with the inner product. This means we have the inner product of the curl of V with n. So this is the component we calculate, and then we have to put that into the direction of n again. In other words, this scalar times n is exactly the component of the vector we want to have. And there you might immediately recognize the second part here. N into the determinant was the definition of the volume form of M. More precisely, we also need J star, but this one we have discussed at the start of the proof. So there we have it. This is the volume form of M, and the whole thing is what we find in the formulation of Stokes' integral formula. So after all this work, we can eventually go to our integrals. And as already mentioned, the first on the left-hand side is exactly the integral over d omega. And of course, this is quite nice, because exactly there we can use our generalized Stokes theorem to go to an integral over the boundary. So as we have learned it, this is just the integral of omega over del m. But as always, to be precise, we should also add our pullback of the inclusion map. In fact, this one is important because we can use exactly the same projection idea as above. Indeed, we actually already consider an inner product here anyway. So the idea here is that we also can project the vector v onto the tangent vector t. So we have a similar picture as before. Here's our unit tangent vector t, and now we consider v as an arrow at the same point. And then the only thing we do is to decompose it into two parts again. So as you can see, one component is orthogonal to the tangent space on the boundary, and the other one lies in the tangent space. So maybe let's call the one Vt and the other one Vn. And moreover, since Vt is our standard orthogonal projection onto a vector, we can just use the inner product again to calculate it. As always, it's just V inner product with t times t. Okay, so this is really nice, and now we can look at Vn, which is orthogonal to the tangent space of the boundary del M. This means if we apply a tangent vector here and calculate Vn with this tangent vector in the inner product, we definitely get out 0. This means we can also just write that Vn in the inner product with these 1 forms gives us simply 0. So again, the orthogonality here simplifies our formula on the right. Namely, we don't need the component that is orthogonal to the tangent space, but just the one that is a tangent vector. And by the standard formula, this is just V in the inner product with t times t. However, this t now also goes into the inner product with the 1 forms. And in fact, for this combination, we already know that this one describes the canonical volume form on the boundary. Indeed, we also need the pullback for that, and then we get the volume form, and only V times t in the inner product remains. And now finally, as you can see, this is the full formulation of Stokes' integral theorem. So the proof is done, and now you know why the curl comes into this classical result of Stokes. In short, it's just a special case of the exterior derivative of a differential form that can occur in R3. And that's the reason why Stokes' integral theorem only makes sense in R3. And in order to see that, I would say let's look at an example in the next video. So I really hope I meet you there again, and have a nice day. Bye bye.